We pick up where we left off last time, looking at what the basic theory of plate tectonics is all about. This is a plate tectonic map of the Earth. Plate tectonic theory says, in brief, this, that the lithosphere, the top 100 kilometers of the Earth's surface, is made up of about a dozen large plates and many smaller ones, and that these plates are constantly in motion with respect to each other. Now I want you to notice a couple of things as we look at this map. First of all, notice that not all plates are completely in the ocean or completely on land. In fact, most of them, like the North American plate here, have some oceanic and some continental parts to the plate. Also, there are plates that are completely in the ocean. The Pacific plate and the Nazca plate are two examples of plates that are purely oceanic. Another thing to pay attention to is the location of mountain ranges. You can see that mountain chains tend to be parallel to plate boundaries and near them, like the Himalayas here and the Eurasian plate, and the Andes in South America, and the Japan island chain over in the Western Pacific. And finally, let's look at mountain ranges and note that there's a strong correlation between continental boundaries that are plate boundaries having mountains like North America, and then continental boundaries that are not plate boundaries being much less mountainous, like the east coast of North America. Take a look, pay attention. You're going to be looking at this map often. So now we have a model where there are a dozen or so really big plates on the Earth's surface, and they're moving around at all times. And so the real action is happening at the plate boundaries. That's where you get all kinds of tectonic processes that help shape the Earth as we see it today. So let's look at those plate boundaries. There are really only three possibilities if two massive plates are moving. Either they're moving apart with respect to each other, or they're coming towards each other, or they're sliding past each other. Where plates are moving apart, like the top diagram, we call that a divergent plate boundary, and the mid-ocean ridge is an example of that. We've looked at spreading centers where new crust is being formed at the center of a ridge. Where two plates are coming towards each other, that is called a convergent plate boundary, and in this case, this is one type of convergent plate boundary called a subduction zone, where one plate goes underneath the other. And finally, there are boundaries where the two plates slide past each other. They're neither getting destroyed, crust there is neither destroyed nor created, and those boundaries are called transform boundaries. You've heard a little bit, we've talked about continental crust versus oceanic crust, and here let's talk about that again because it is important in plate tectonics. The continental crust is made up predominantly of more silica-rich rocks and minerals, for example, granite, and has an average density of about 2.7 grams per cubic centimeter, whereas the oceanic crust is made up predominantly of less silica-rich minerals and rocks like basalt, and it is more dense, 2.9 grams per cubic centimeter. And therefore, the oceanic crust will subduct underneath the continental crust when they meet. The mantle has an even more dense is even more dense, made up of minerals and rocks that have a composition that is even less rich in silicon and has a density of 3.3 grams per cubic centimeter. Oceanic crust is thin. Continental crust can be quite thick, especially under mountains. So just as a review, now we're looking at a three-dimensional cutaway of what some plate boundaries might look like. In the very center, we have upwelling mantle convection that is bringing heated rock to the surface at the mid-ocean ridge and forming a divergent plate boundary. And then off to either side, you have that oceanic crust, that basalt, going underneath, subducting underneath the continent. And as that crust disappears under the continent and moves its way down towards the mantle, it melts and it becomes part of the mantle again. This subduction is really important because Hess told us that we're making new crust at the middle of the ocean ridges at all times, but of course Earth is not expanding, and so it has to be being consumed somewhere else, and that place is subduction zones. Let's look at a lava lake just to get a quick little view of what plates might look like on a hot convecting mantle. So as you watch this, you can see these plates forming on top of the lava lake, and then watch the boundaries. See where they're sliding past each other, where one is going over the other, where the new rock is being created at the edges. Very much like plate tectonics, but a lot faster.